It's a very simple lecture. Most of it, I believe, you know from previous classes. So I will cover mostly doping for junction formation and doping for threshold adjustment. But before we go for doping, before I'm going to show you the details how to dope semiconductors, let's review a little bit the structure of an MOS transistor. And this is a structure of advanced MOS device. I'm going to show you this device today, and later this lecture I'm going to show some even more advanced devices, but this is a pretty advanced device. You can see here a junction, and this junction the blue layer in the street side, which is the alloy, a combination with metal and silicon. It can be nickel silicon compound, which is called nickel silicide, and it can be titanium and silicon, typically titanium disilicide, TiSi2, can be cobalt silicide, and so on. The reason we use silicide to reduce this resistance, this is the serial resistance, can be significantly reduced by the presence of the silicide. This is the gate, and a typical gate is conducting, made of polysilicon, and a very thin layer of silicide on top. On the side of the gate, there are two spacers. The yellow sections are the spacers. And the reason is that during the process, first we produce the gate, then we implant here a low doping, this area and this area. Then we introduce the spacer and implant this heavy doping for the source and the drain. So I'm going to show you today the way we produce the source and the drain and these shallow implant regions. This is even a better slide of an MOS device. Let's say it's an N-type substrate, and the structure is a retrograde. If you remember, I told you from the previous lecture that by ion implantation, I can generate a profile which is called retrograde. Retrograde means more doping here than here. And you do it by energetic ion implants, so the implant goes to this region, and this one is lower doping. This area is N plus and N plus. This little area here is N with lower doping. Now what you usually see in modern transistors, that next to the junctions you put this red region. This is called a halo, or some companies call it pocket implant. And this pocket implant is done, for example, if you implant in an angle. The ions are coming in this direction and you implant them here, or the ions are coming in this direction and are implanted here. And you need this area because, if you remember, this is a junction. So the depletion layer in this region will be smaller because you increase the doping of the substrate. And the depletion, this is a junction, N plus N. And here you have a depletion layer. But you don't want this depletion layer to be too big because it will affect the structure here. Same as here. You can also have some leakage current going in this direction. So you introduce here heavier doping to limit the depletion layer here. Now you don't introduce this doping everywhere because this also increases the capacitance of the junctions, and it also produces some. If you will introduce heavily doping here, it will also increase the leakage current of the devices. So you introduce this doping only here. So this is called a halo structure or halo structure, or in this region is called pocket implant. Now this is a retrograde well. In a retrograde well, if you have a uniform well is the doping, this is the doping versus distance. In a typical structure, this well is almost constant, but in a super steep retrograde well, and for example, if it's done by arsenic, you introduce a doping which is actually going down next to the surface. And you can do it only with ion implantation, because you implant this region and not this region. I'm showing you some other interesting structure. This one I took from another company. It's called a super hollow profile. And this is a relatively old design from 1998 by Tower and his company, presented in the IDM meeting. This is a quarter micron technology. This is a source. This is the drain. And the plot here is of the doping. What you see here are the contours of the doping. So the source here, this is 2 times 10 to the 19. 1.5, 1, and 5, 10 to the 18, and 0, so this is the junction. So this is the junction. What you can see here, that the junction here starts here and goes down. You see that the slope of the profile is from here to here. But on the side here, the slope is much deeper, because what they do, they implant here a P-type, and here they implant a P-type in this region and this region. And this makes the slope here steeper. And what happens, this structure that looks like this shape has a higher doping here. This is 1 10 to the 19. This is 5 10 to the 18. So this area is P+, and this area is P. So this structure is called, and you notice that they put the P+ here on the side of the junction, not here, not here, and not here. Here is lower doping. Now the transistor itself is here. This is where you have the channel. So what I want to show you, that today in modern transistors, the junctions are very complicated and usually two-dimensional. Yes?
Before you said that you implant higher doping to make the depletion area smaller, and here the gradient is lower. I mean, the higher doping is on the side and the middle is...
So what you do, the junction
itself is lower doped.
The junction itself here is lower doped?
Then
No, what you do, the question is, what exactly happening here? How we get this high doping here? You implant in an angle from here, and you bury the peak of the implant here. And this is for the P. The N-type, you put the peak here. So in this, if you cross along this line, you got P plus N plus here and P plus here. So you got the steeper slope here. In this area, this is N plus and this is only P. So the slope is not that steep. I'm sorry? The main motivation is to have, from here to here, a small depletion layer. And from here to here, you don't care. Actually, you don't want... The reason you want a small depletion layer, because if depletion layer here, you see, this is the drain. Let's say you put a bias on the drain. If you put a bias on the drain, the depletion layer will increase. And if the depletion layer from this area will meet the depletion layer from this area, you will have a punch-through. Then you will have current flowing from here. So you implant here a P+ as a barrier to prevent current flowing in this direction. However, you don't want to put P+ everywhere, because you don't want N plus P+ junctions, because they are very leaky. If you remember the equation for leakage current in junctions, for heavier doping, you have more leakage for junctions. Another reason, if you have heavier doping, you have more defects because of the ion implants, and if you have more defects, the minority carrier lifetime becomes shorter, and then you have... So, doping. What is doping? Doping, I showed you some examples of rather very complicated doping schemes, but I have to tell you that these transistors that I showed you are about 10-year-old, so I'm going to show you later even more complicated doping. So this is... So you have here, what is doping? Introduction of dopant into the silicon wafer. and you deposit either from the gas phase or by ion implantation. And we discussed ion implantation in the last lecture. A high temperature process drives the dopant atoms by diffusion. Now, typical dopant concentration versus depth. When you, if I want to teach you about doping, I'm going to show you profiles which are typical profile. For example, this is the surface. This is the doping, starts at a few times 10 to the 19. As you go inside, the concentration goes down. When the concentration of the dopant here equals to the concentration of the substrate, this is the junction. So this is dopant concentration depth after typical diffusion of opposite type dopant, for example, N into P or P onto N. So this is what you get. You get a region which is heavier doping, region with a lower doping, and a junction. So this is a typical profile. Now, because the typical profile drops down exponentially, the plots are typical log scale in the y-axis and linear in the x-axis. What kind of dopants we have in silicon? The substitutional doping, where the phosphorus replaces silicon, or boron replaces silicon, or arsenic, aluminum, gallium, antimony, and germanium, they are all can replace silicon. So they are substitutional. Oxygen, gold, iron, copper, nickel, zinc, magnesium, practically most metals, they interstitial. They don't replace the silicon, but they are sitting between the atoms of silicons. Let's imagine if you have a perfect crystal, and in this crystal you have this atom which is a foreign atom. If you hit the structure and hit the structure and hit the structure, it's possible this will atom move here and this atom will move here, and at the end of the day you will get the atom moving one step to the right. But in order of this to happen, you need the atom to squeeze side by side. If you want this atom to move through this narrow channel, this has to move this, it will move this. It's like if you are in a train and everybody around you is very crowded, if the train is very crowded, you cannot move. But imagine that next to you there is a vacancy, missing atom. Then the dopant can move to the right. Actually, and the dopant moves to the right, the vacancy moves to the left. So this is called diffusion via vacancies. Now, if you do the thermodynamic calculation, this process is much more favorable than this. This is a difficult process. This process occurs much easier. Now, it's possible that the next step, let's say this atom moves here. What is the next? What can happen next? There are four possibilities. One possibility that this atom will move back, and then nothing will happen. Basically, this motion backwards will cancel this motion. Or this atom will move here, and then it actually will have a motion to the right of the black atom, or this will move here, or this will move here. So if you have four possibilities, one cancels the previous motion, and three are actually keeps the motion. So when you calculate diffusion, there are two things you have to pay attention. One is the probability of having a vacancy. The second, if you have a vacancy, is the probability of this atom that will move here. Because this atom can move here, or this can move here, and this can move here, and this can move here. So only one motion is counted. Or, after the motion, this can move back, but there are three other possibilities which are in favor. This is called coordination. Basically, the motion is not just the probability to jump, is to look at all the possible mechanisms and to choose the one which actually contributes to the total motion. So I'm not going to teach you too much about how to calculate diffusion, but to understand that when you model diffusion, first you have to calculate the probability of having a vacancy. Second, the probability of a net motion to the right, which depends on the geometry of the system. Now this crystal is cubic, it's very simple, but the crystal of a silicon is diamond, and the diamond is a three-dimensional structure, and it's much more complicated. So the coordination numbers can be, it's not so simple to calculate them. Now you have other diffusion mechanisms, not only by vacancy. You can have a combination like interstitialcy. For example, this is an extra interstitial next to an atom or dopant in the right place. But it's possible that if you hit, this will move here and this will move here. So the next step, the red atom will kick a blue atom. And this, again, this is called the interstitialcy mechanism. As you can see, it's a little bit more, and it requires more energy than the vacancy, but it's still possible, especially at high temperatures, because at high temperatures there is more energy for such mechanism to happen. And it also can happen in situations where there is a different size between the dopant atom and the silicon. Because I showed you here that the blue atom and the red atom are the same size. But what happens if this atom is much smaller than this one, or much bigger than this one? So when, imagine that the red atom is a small atom, and if it's a small atom, this blue atom will move slightly inside. So you will have here some strain field inside the lattice. So there is not only the energy of creating a vacancy, but the elastic energy of the crystal next to the atom inside the crystal. And you have to take all this into consideration, because what determines the jump of the atom is you need how much energy you need to move the atom from one place to another place. This energy can be chemical because of the bonding, can be also mechanical because of the lattice itself is holding the structure. And when you have, for example, a vacancy like this, the structure, the actual structure does not, imagine you have a crystal. Every crystal, every atom holds its neighbors. Now, you move one atom out. So this atom, this one is holding it, this one is holding it, this one is holding it. There's nothing from this side. So this structure will open a little bit. So next to a vacancy, you generate a strain field, a mechanical strain inside the lattice. So you have to take into consideration this mechanical energy. Again, I'm showing you only the principle, not the actual combination. You can also, another mechanism called kick-out. And another famous mechanism is the Frank-Turnbull, where you have a combination of kick-out is similar to the interstitialcy base practically, but the Frank-Turnbull is when you generate a pair. This atom moves from here to here and stays, and you have a pair of an interstitial and a vacancy. And it's possible. Other diffusion mechanisms, the Frank-Turnbull mechanism, when the dopant can be in the vacancy, but the dopant next to a vacancy is more stable than a dopant not next to a vacancy. So it can actually move. This pair of defects can move. Yes? It's interstitial is basically kick out. Yeah, sorry. It's just more detail here that this atom kicks away this atom and generates an interstitialcy. And the Frank-Turnbull, when actually you have a combination of interstitial and vacancy together, a couple. So diffusion in solids, to understand diffusion in solids, I explained to you first that diffusion is a molecular kinetic process that leads to homogenization or mixing of the chemical component in a phase. The diffusion occurs in the same phase. It can be in water, like you add dye to water. So if you have high concentration of dye here, so the dye is slowly diffusing into the structure, and you have a partial mixing, and the end is homogeneous. In semiconductor technology, we are not dealing with infinite time. We don't get homogeneous structure. We deal with this type of situation that we have partial mixing. We introduce the dopant next to the surface and it stays next to the surface. We are not dealing with complete homogenization. So this is function of time. The diffusivity is a thermally activated process that follows the well-known relation. You have a constant called the diffusion constant, and the diffusion constant describes the relation between the average distance during a given time of the diffusion. If during a given time the dopant is moving through a large distance, then the diffusion coefficient is high. When it moves through a very short distance, then the diffusion coefficient is low. Now there are a few definitions to diffusion coefficient. One of them is based on the random walk model. Imagine that you have a pub, and there's a drunk person next to the pub, and the drunk person is doing the following. He wakes up, then by random takes some distance, delta x, and then falls down. And it takes tau seconds between when it starts, then it falls down. Then it wakes up, of course he's completely drunk, then by random choose another direction, then falls down. So if you look at this structure, then you calculate the average in every distance, in every motion, it passes a delta x, and it takes tau seconds. So the relation between the mean square of this distance, delta x square, divided by the time, is a diffusion coefficient. And it can be proven that it's a constant. You know that the diffusion length, the total travel, you remember from semiconductor introduction to semiconductor devices, that the average length, the diffusion length, is proportional to what? Square root of time. You remember diffusion length is square root of d over time. So the relation between the average distance square to the time is the diffusion coefficient. This is actually it's not only the result, but it's also one of the definitions of diffusion coefficient. Now you can prove the diffusion coefficient depends on the temperature, and the higher the temperature, the more active, the faster is the process. And you have an activation energy delta E. D0 is a prefactor, delta E is the activation energy, and Rp and Rg is the universal gas constant, and T is the temperature. If you take delta E in electron volts, which is very common, then you replace Rg with kT over Q. And D0, typical units for T0, is centimeter square per second, because D0 has the units of distance square divided by second. The units of D are centimeter square per second. Or you can take it in meter square per second or others, but typically we use engineering units with centimeters. Now let's give you let's give analytical solutions to the diffusion equation. If you have dopants inside the material, then we know that the concentration follows the diffusion equation. The diffusion problem, the concentration follows the diffusion equation. The first derivative of the concentration is diffusion coefficients times the second derivative versus x. And if you take the diffusion equation for, let's say, a common problem is, let's say, in a region when there is nothing here, and next to it there is a species with a concentration, let's call it CS. And now when you hit this structure, here we have high concentration, here you have low. So material will diffuse from here to here. This is very common if you have a semiconductor, and next to it there is some gas phase, and the dopant is diffusing from the gas phase into the semiconductor. The solution for this case is the concentration and this is the coordinate z inside versus and time, is some surface concentration, because we introduce a surface concentration Cs, and the Cs is typically the solubility of the dopant inside the semiconductor. The solution for the diffusion equation here is the boundary condition. Initially here, concentration is 0, Cz0 equals 0. Concentration at x equals 0 is constant, is equal Cs, and the concentration at and the function is decaying, which means it's infinite. If we go infinite distance, the solution will be 0. So the solution for this equation is the error function equation, which looks like this. This is 1, 0.1, 10 to the minus 2, 10 to the minus 3. And this is the diffusion from a constant source. This is the solution for the diffusion equation from a constant source. So if we want to make a junction, we can hold the semiconductor in a gas, and the gas will diffuse inside the semiconductor in forming this profile, which is an error function. This was the technology that people used before ion implantation. They introduced gas, the dopant from a gas phase, and this was a diffusion from a constant source. When you diffuse dopant into semiconductor, you can ask yourself how many atoms enter the semiconductor. So what is how many atoms? We call it a dose. And the dose is the number of atoms per centimeter square. Is the integration, and here is a typo here. It's the integral between, I think I have to correct it, and we can do it in real time. The integral, so I apologize, there's a typo here. The integral from 0 to infinity Czt dt, it's how many atoms enter the semiconductor. So the integral is between 0 to, it's a dz between 0 to infinity. And the solution is very simple, because it's an error function. The integral of an error function is the concentration at 0, but the concentration at 0 is Cs times square times the diffusion length, square of dt.
Shouldn't it be a function of z?
Q0, no, this is exactly what I told you. I have a.
No, because the integral q is a function of t. So the integral.
This is exactly what I told before. Let me correct it in real time. So this is, let's see, I tried to do it. So this is integral infinity. And I should put here blank. And here it's dz. And excuse me that I'm not using the same fonts, but you have to excuse me. But you can appreciate this is even, let's do the same font even, just for the order, Times New Roman, and even give the right size. Almost. So this integral between 0 to infinity, Czt dz, and then it's a function of time. Now, this is one possible diffusion, that you diffuse from a constant surface concentration. However, if you remember, when we do ion implantation, first we introduce a dose into the silicon, and then we diffuse, but we diffuse from a constant dose. So the number of atoms is constant, not the concentration. So the solution, you have to solve with the different boundary conditions. For example, one boundary condition in the surface, C0, let's say initially we diffuse from a constant dose, so initially there is nothing in the semiconductor. We also assume that nothing is coming out from the semiconductor. This is a typical boundary condition, that you have the profile, and you say that initially I have a constant dose, and the dose is here next to the surface. and the dose, the total amount Q of atoms per centimeter square is next to the surface. You can call it a delta function. It's a very constant, very definite number of atoms. And after a while, this diffused. The atom diffused inside. But we assume that next to the surface here, nothing is going out because they all diffuse inside. And because of that, because there's no diffusion outside, the derivative equal to 0. Initial condition also derivative equal to 0. And this is the boundary condition, C0t equals 0. Again, the profile goes to 0. And what's important, the integral of the concentration is constant because the total number of atoms is constant. Again, we have to check this boundary condition. Why did I put here this C? I think it's also a typo here. It's the derivative over x equals 0. So it's the boundary condition. Solution. Diffusion from a constant source. This is a solution. The solution here is unlike the previous, it's not error function, it's a Gaussian. And you can calculate, you see the concentration at the surface is going down. Again, in this class, I'm not going to teach you much about this. And the reason, this is a very old material. Old, I mean 10, 20 year old. Today junctions are slightly different, and the main reason is that today junctions we deal with very high concentration, and I neglected something which is very important. I assume that D is constant, independent of distance, independent of concentration. However, D is a function of concentration. And therefore, the solutions I gave you are suitable only for very low doping, which is not the case for source and junction. Now, I summarized here in the following slides the old diffusion process when before ion implantation, typical diffusion has 2 steps. Diffusion from a constant. So this is kind of an example for a diffusion process where you can have a diffusion from a constant source. This is called predeposition, and continue with the drive-in step, which is practically diffusion from a constant source. I will skip these transparencies, and I will skip the diffused junction. I would like to move on, and the reason I gave you here 3 slides, just describing this diffusion process, where you have an initial diffusion from a constant source and then a drive-in step. I'm going to skip this process because today the diffusion is from ion implantation. And the actual initial condition if this is concentration versus x, after ion implantation, the concentration, this is the initial condition, and you have to solve the diffusion equation, which is with different boundary conditions. I showed you solution from a constant source. I showed you solution from a constant dose. But today you can assume a constant dose, but it's only an assumption because we never have a real delta function. For example, you can solve in this profile. This is the initial condition. If we heat it up, we'll have diffusion in this direction and in this direction. So the profile will go like this. I'm just guessing. And so if I try to solve the diffusion equation just by thinking how the solution should look, it's very complicated. And you really need to solve the diffusion equation based on the real boundary conditions. But I showed you some examples, as just examples. Questions?
Physical justification for pure Gaussian function for the diffusion?
This is why you get a Gaussian function here and an error function. This is actually How do you say the generating functions for the diffusion equation? I said the eigenfunctions of the diffusion equations are Gaussians and their integrals. So these are the natural solutions for the diffusion equation. It's a Gaussian. Now there you have other fields. You have other effects in the semiconductor. Let's say that you have a gradient. Let's say you have a look at the following situation. This is concentration versus X, and this is X. And let's say the profile is like this. And let's say this is N-type dopant, N-type. And the substrate is P-type. And I hit this structure, and because this is N-type dopant, I have a lot of electrons here. But the electrons diffusion is much faster. So you have here electrons which are diffusing slightly faster than the atoms of the N-type dopant. But what is the charge of N-type dopants? It's positive, plus. So there is electrical field in this direction which enhances the diffusion, because we have dopants, but we also have electrons and holes. And because the dopants generating electrons, and because the electrons are diffusing faster than the dopants atoms, they generate an electric field. And the electric field practically generates a field that enhances the diffusion. This is called field-enhanced diffusion. If you learn from basic semiconductor physics, the electric field is T over Q 1 over C dc over dt. This is taken from the introduction to semiconductor physics. You see that the diffusion coefficient is equal to d times 1 plus eta. The actual diffusion in a steep profile is also enhanced by electric field. Another possibility, yes. Let's do it again. This is concentration versus X. This is X. And let's say this is the profile. And let's say this is N-type dopant. And because we have N-type dopant, we have electrons. And because we have electrons, the electrons tend to diffuse into this direction. Right? We have electrons here, E minus. And here we have a lot of electrons. Here we have a little number of electrons. The electrons also want to diffuse. Now, electrons diffuse faster than this N-type dopant. So what happens? We can calculate the total current of the electrons. If you remember, it's Q times their mobility times the concentration of the electron, which is C, times electric field, plus Q times D times their diffusivity times dN. We know that C equal N, because the number of electrons is equal to the number of the N-type dopant, dC over dx. But what is the total number of electrons? What is the total value of the current of the electrons? What is the total value of the current of the electrons? It's 0. Because this sample, they are going nowhere. It's not connected. It's an open circuit. So if you divide by D, you can calculate E, the electric field. And the electric field is equal to D over mu, which is KT over Q, 1 over C times dC over dx. Now, this electric field is in this direction. And the reason, because here the electrons want to go into this direction. So if the electron wants to go into this direction, it means we have electric field. We need to generate if the electrons want to diffuse in this direction, we need to generate electric field that will bring them back. So electric field that brings back electrons from here to here is electric field in this direction. And because the n-type dopant are positive, they will go into, and their diffusivity will be enhanced. And the reason it will be enhanced because we're actually generating a dipole here. Minus, plus, minus, plus. You can think about it as there's a very small dipole which actually is pulling the atoms. This is called field-enhanced diffusion. But there are other effects that people discover. People discovered that if you have this structure, and for some reason there is oxygen here on the surface. There is oxygen near the surface. Now oxygen reacts with silicon. People found out that if there is in the same time oxidation and diffusion, the diffusivity can change. The diffusion coefficient change. And this is called diffusivity under oxidation is the intrinsic diffusivity plus some delta D. Some delta diffusivity. Which means if this is a very rapid oxidation, then the diffusivity is faster. And the reason is when during the oxidation, if this is silicon, you react silicon plus oxygen become SiO2. So this reaction is near the surface. So this reaction consumes silicon. It takes silicon from the lattice. So it's very possible that it will generate vacancies near the surface because it does not take the atoms, all of them, at the same time. So it can generate vacancies. Now, if you have here a lot of vacancies, and here a lot of vacancies, and here less vacancies, what will happen? The vacancies will diffuse also. Then you have to solve the diffusion equation from the vacancies also, which is also the same diffusion equation. But the concentration of the vacancies affect the diffusivity of the silicon. So in order to solve the real case of diffusion of atoms in silicon, you have to solve the diffusivity for the atoms in silicon and the diffusivity of the vacancies, which is a function of some stress or other effects on the surface. Now it's possible, by the way, that if you do vacancy, if you do oxidation, reaction with oxygen, the diffusivity increases. However, if instead of oxygen you introduce NH3, ammonia, now NH3 reacts with silicon, NH3 plus silicon, generate Si3N4 plus hydrogen coming out. Now you balance this equation. So 3 silicon here, so this is 3 here, and N4, so this should be 4, and 12 and 6 H2. So this reaction generates a thin layer of nitride. It's very common, like in flash memory applications, and it's a known reaction. It's a very useful reaction. But if you do this reaction, the diffusivity is going down. Because this reaction actually consumes vacancies, reduces the number of vacancies in the structure, and consumes interstitials. So it reduces the number of defects. So in this case, alpha is this coefficient. And by the way, the change of the diffusivity depends on the oxidation rate, on the reaction rate. So some power which is found experimentally. So I will skip this. Okay, I will not skip. So this is what I really wanted to show. So excuse for the previous slides. Now I'm going to show the actual diffusion step. First, in the practical diffusion process, you dope by initial doping by introducing the dopant inside the silicon, by ion implant, mostly by ion implant. The second step is called drive-in. Let's say the red area is the concentration of the dopant. You see here, this red area is the concentration of the dopant right after ion implantation. When you heat it up, there is a diffusion, and then you got this orange area, which is actual junction. Now the diffusivity follows the diffusion equation with a constant D. D is the concentration, is the diffusivity. The diffusivity depends if I introduce some oxidizing species on the surface. If I put oxygen and then I oxidize the surface, the diffusivity will go faster. Now everybody is doing ion implantation and annealing. In the past, people used solid gas phase diffusion. It's not so common anymore. Maybe used for solar cells or other less demanding processes. And ion implantation is done in room temperature, very good dose control. You can implant 10 to the 11 to 10 to the 16 atoms per centimeter square. Very accurate depth control. The problems, you introduce damage, you introduce dislocation, which is defects, and the implant channeling may affect the profile. So if we have to overcome it, if you can overcome this, we have a good process. Another interesting parameters is the solid solubility. When you introduce arsenic into silicon at like 1100 degrees, you can introduce 2 times 10 to the 10 to the 21. However, if you want to introduce aluminum you cannot put more than 2 times or 3 times 10 to the 19. So aluminum, it's a good dopant, but the problem, you cannot use it for high-level doping. And this is why everybody is using boron and are not using gallium or using aluminum. Aluminum, gallium, boron are all atoms which are p-type dopants, because they all have 3 electrons in their valence. They have 3 valence electrons. They're all in column number 3. I think the order is boron, then aluminum, then gallium, if I remember well the order. The problem is gallium and aluminum are not so used today, is because you cannot make heavy doping. With boron, you can have much higher doping. Same as arsenic. Arsenic has the highest doping today, is the most popular dopant today. Phosphorus is also used in many cases, but definitely antimony is not so. It can be used, but it's not so bad. 10 to the 20 is not so bad, and you can buy wafers with antimony actually today. Now you have to. One of the things you have to understand, there's a difference between how many atoms are in the lattice and how many atoms are electrically active. When you make junctions, when you produce junctions, you care about the number of atoms, and this is electrical solubility limit. This is, for example, this is arsenic and silicon. And you can find that, for example, at 1000 degrees Celsius, the number of electrically active arsenic ions is about 2.5 times 10 to the 20. If you go to the previous slide, you see at 1000 degrees, there is about 2 times 10 to the 21 atoms of arsenic in silicon. So you see here that a lot of arsenic atoms in silicon are not electrically active if you go to very high concentration. They usually generate some complexes of silicon arsenic 3 or some other structures in the silicon, which is not what we call substitutional structures. They are not replacing silicon atoms. They are in very high concentration. This is the limit, and this is arsenic and silicon. Now, and this is the practical limit of achieving very heavy doping. Now, what people are trying to do now is to go to higher concentration, because you know that in some cases you can introduce atom above solid solubility if you are in a metastable state. You can, for example, implant very high dose and do the annealing so quickly, So the atoms will not generate the structures which are not electrically active. So some new processes today, for example, there is one process that you actually illuminate the surface of the silicon with a very, very rapid, very short laser, pulse laser. You melt it and then it cools down immediately. So it's called like laser induced melting of the surface. The surface melts and cools down. So you can think, and this is a big problem in material science, how to introduce dopants above the solubility limit.
Don't you create stress?
You create a lot of stress, and then you can, and then the reliability will go down. It's a good point, is that this is still a good process to do it. Still does not exist. There are some processes that are available, but they introduce defects, and then you have to decide what do you like more. Now, I did not. This slide actually should be. It's in the wrong place, but we all know Fick's law. So the flux depends on the derivative of the concentration. Just to show you some facts now. This is the diffusivity, the actual value of diffusivity of arsenic, phosphorus, indium, boron, and antimony in silicon. This is the diffusivity in centimeters squared per second versus 1 over T. Now, if you look at this curve, what can you say about these curves? They all look alike, which means arsenic and antimony, or phosphor, this is indium and boron, all curves look the same. The curves are almost independent of the atoms. And the reason is the diffusion depends on what? On the concentration of the vacancies. So what determines the diffusivity is not the atoms, it's the concentration of the vacancies. And the concentration of the vacancies depends on the temperature with a certain way in silicon. So the diffusivity of atoms, there are two families, but they all have similar slope, and they all are very similar. And this is the reason. This is kind of experimental evidence that the diffusivity is independent of the time, or not totally independent, but it's not strongly dependent on the type of the atom, but depends on the concentration of vacancies in the structure. Now let's give you some practical examples, and let's try to solve a practical situation. Let's say this is an N-type dopant. This is the initial concentration, and this is arsenic dopant, and this is the initial concentration. It's very high here, about 5 times 10 to the 20 here. And this is after ion implantation. And the blue is the concentration of the boron. So this is in order to make a junction, and the initial junction depth was here, which is less than 0.1 of a micron. This is a quite shallow junction. It's about 600 angstrom, 500, 700 angstrom. Now you take this structure and anneal it, and this is what you find. You find this is the dopant, this is the concentration of the arsenic, and it actually follows diffusion equation. I will show you later. It's almost here when you solve the diffusion equation, you find here it falls very nicely, but here it's not. But I will talk about it later. But look at the boron. Boron here, the concentration went down. It's like some of the boron diffuses from here to here. And the reason this area has more defects. This area has more defects, more vacancies, and the diffusivity in this area is higher. So some of the material diffuses from here to here. So the junction actually, instead of being here, it's being here, which is luckily almost the same position, but if you calculate the doping level by measuring the junction capacitance, you find out that it's slightly less. The doping level is less, yes.
So
Initial.
of the boron.
Yes. And this is typical near junctions. You find a lot of anomalies because near junctions you have areas with high defect density, low defect density, high concentration of vacancies, low concentration of vacancies. Because here you have a lot of dopant. Dopants here is a mode almost 6 times 10 or 5 times 10 to the 20. And because you have a lot of arsenic atoms that generate mechanical stress, and the concentration, they generate more defects near the surface. Now, what you find out in arsenic, another thing, that if you look exactly on the profile of arsenic, and you plot the profile of arsenic, and you plot, and this is a concentration, this is the red one, this is the concentration, solution to the diffusion from a constant source, it's an error function. If you plot arsenic profile, you find the blue line, not this line. And the reason, it was found out experimentally, the diffusivity of arsenic and boron and phosphorus, it's like some D0 plus D1 and N over, let's give you the exact expression later. D is a function of N over Ni to some power, P. What people found out? They found out that the diffusivity depends on the concentration. In some dopants, it's proportional to N over Ni, and in some dopants, it depends on N over Ni square. So the actual, when you solve the diffusion equation, the solution is not anymore error function. It's not a Gaussian. It actually looks more like this. This is if it's a linear function or if it's a square function, which is good. It's good because you get steeper junctions. And the reason here in this region, the concentration is high. So the diffusion here is faster. In this region, the diffusion is low. Let's say this is Ni. So in this region, diffusivity depends on the concentration, so it's faster. Here, diffusivity is slower. So what you got, the actual profile in arsenic and boron does not follow the classical solution of error function, but there's no analytical expression to this. I'm not going to give you the exact solution for the diffusion equation, but the junction is much steeper than what you think. And the reason, and I will skip the 2 slides, is the following. The reason is that when you look at actual vacancies in silicon, the situation is more complicated. Because the structure is not ideally, it's not a 2D, it's a 3D, and the vacancies and the interstitials can be charged. For example, this is a silicon diamond structure. This is a vacancy. Here we miss one electron, one atom. The atom went somewhere. Now remember that you have here other silicon atoms, and here we have some missing bonds, because initially there was an atom there, but the atom went away, but still you have 4 electrons coming from the sides. Initially there was an atom here, so depends what happens. We have 1, 2, 3, 4 bonds, and these bonds can be either full with electrons or empty or partially full. So this vacancy can be charged, and you can measure this charge, because if it has 1 electron, it has kind of a spin. 2 electrons, it's a different spin. So you measure it by some technology, the technical electron spin resonance, and you can measure the number of this is vacancy in the plus charge state. Darkened bonds indicate orbitals with unpaired spins, which make V plus visible to electron paramagnetic. Sorry, it's not electron spin resonance, electron paramagnetic resonance experiments. So this can be vacancies charge plus 1. Charge plus 1 means there's one electron missing. It can be 0. It can be basically all electrons are basically somehow, all the orbitals are basically making the connection. It's not the most favorable state, but it can happen. So this is a neutral vacancy. Vacancy in the minus charge state, the darkened bonds indicate orbitals with unpaired spins, which make Vi minus visible to electron paramagnetic resonance. So if you have this structure, and here you have only one orbital, and this is unpaired structure, this will be V minus, means there's an extra electron here. So the vacancies can be charged and can be neutral. Why this is important? The problem that it's important because if we want to know if the vacancy is charged or not charged or neutral, it depends on the Fermi level in the semiconductor. If you plot the energy band of the semiconductor, this is the valence band, conduction band, sorry, this is the valence band. Now, these vacancies generate some states. They are perturbations. They are like defects. They generate states inside the semiconductor. Now, if the Fermi level is below, then this state is empty. If the Fermi level is above, this state is full. So these vacancies will have electrons which full if their energy will be below the Fermi level, or depends on the doping. So if we have n-type doping, in n-type doping the Fermi level is high. In n-type doping the vacancies will be either 0 or they will be charged. They will be full with electrons. If we have p-type doping, then the Fermi level is low. Then this energy level of the vacancies will be empty. So the concentration of the vacancies, because we can have 0 vacancies, plus vacancies, or negative vacancies, and their concentration depends on the doping. And because of the concentration of the vacancies depends on the doping, the diffusivity depends on the concentration. Also the interstitials. You have an extra doping here. This is interstitial. This is called tetrahedral interstitial. It sits here inside this void inside the lattice of the silicon. Or it can be a hexagonal interstitial instead of the, depends on where we put it inside the void inside. We can also have point defect interstitials. We can have a silicon interstitial C defect. Both black spheres are silicon. And we have dopant. So we have the dopant and the interstitial is one of the black spheres is a dopant atom. So we have one extra silicon. We have a vacancy in interstitial next to side by side. It can be, and this can be neutral. It can be negative. We can have interstitial which is 0. We can have it can be either acceptor or a donor. If I conclude, I will stop here. This becomes too much a class of material science. But if I can conclude here, the defects are charged. And because they are charged, their concentration depends on the Fermi level. And the Fermi level depends on the doping. So vacancies can gain electron, but I showed you only +1, -1. But you can think of +2, -2, +3, -3, +4, -4. Situation, if you do the actual analysis, it's extremely complicated. You have a lot of type of charge vacancies. And they can gain a hole or lose an electron. The charge vacancies population depends on the location of the Fermi level. And we assume dilute vacancies concentration, each vacancy type assumed to contribute to one component of the dopant of diffusivity. So this is the actual analytical expression. The one expression fits everything of the diffusivity. This is the diffusivity of the interstitials. Di, sorry. This is intrinsic diffusivity. This is diffusivity if we don't assume this effect. This is the diffusivity to the negative charge. This is diffusivity of the doubly charged, triple charge, 4 charge. And this is for the vacancies which depends on n. The part which depends on the whole concentration also has 4 components. Now this, don't worry, this expression is more theoretical. In practice, if you look at diffusion of some common dopants, boron, phosphor, and arsenic, this is the expression of boron in silicon. Boron depends on the holes. And of course, if we deal with diffusivity of boron, we care about concentration of holes, because boron is p-type. So if we have boron, we have p-type semiconductor. We don't have electrons, so we don't care about the other components. Arsenic depends on n. So this is the same expression, but because arsenic is n-type, the function contains only the function of the electrons, not a function of the holes. And phosphorus is more complicated. This is what I want to, before we end this lecture, to show that things can be even more complicated. Let me first finish phosphorus. In phosphorus diffusion, we see one diffusion and a second diffusion. This was discovered actually when people processed bipolar devices. And you can see here that you expect the profile to go like this. So you expect the junction to be here. But the actual profile go like this. And the reason is in high concentration, in this region, actually diffusion is a positive phosphorus ion paired with doubly ionized vacancies. Phosphorus tends to pair with a vacancy and move with the vacancy together. So what happens? Here, it's not just the phosphor. The phosphorus is traveling and the vacancy is traveling behind it. So they are dependent motion. But this occurs only at high concentration. So what happens here? Here, this pair of phosphor and vacancy dissociate. So suddenly, here you have a lot of vacancies. And then we have much faster diffusion inside. Because if you remember, if we have high concentration of vacancies, we have fast diffusion. So this is called, by the way, the emitter push effect, because this was discovered when people developed the emitter process for the bipolar devices. Luckily, in CMOS, we don't see much of it, but you have to remember that phosphorus diffusion is coupled with the vacancy diffusion. And this is the actual expression. It's a very complicated expression. And it's interesting because if, for example, you diffuse arsenic and phosphor together, you sometimes can find even more complex structure. And I will keep you, I think I'll end the lecture here, try to explain this profile. And this is the end of the lecture of diffusion and charge formation. And if you want to know more, this is the end of the lecture. If you want to know more, I can give you some, it's basically the references. Any questions before we end this lecture? Yes, one last.
N on Ni, it's the N of the doping or
N of the doping, and Ni is the intrinsic carrier concentration in the semiconductor.
And if the semiconductor is not pure, so the Ni changes or?
No, Ni is intrinsic carrier concentration. Ni is Ni square is Nc times Nv minus Q E gap over Kt. This is it's intrinsic number. It's independent of the semiconductor of the doping.
But if they have like a bulk which is a lightly p-doped, doesn't it affect something?
If it's a lightly p-doped, then the Fermi level is below, and then more vacancies are positive. Then we have more If it's lightly p-type, it will not be effect. But if it's a heavy p-type, then we have, in additional to the neutral vacancies, we have also more positively charged vacancies, and then diffusion will be faster because we have more vacancies.
So it will be in the DI in this?
You're talking about in boron, right? Boron, lightly p-type. This is if p is smaller than listen. We are talking diffusion at 800, 900 degrees Celsius. At this temperature, Ni is 10 to the 18, 10 to the 19. So only when the concentration is more than 10 to the 18 or 10 to the 19, then we'll have this effect. So it's not, this effect does not occur for lightly doping, only for heavy doping. Because Ni at the diffusion temperature is very high. Okay, this is a little confusing lecture, but we go to break with, try to explain this slide and we continue. This is the end of lecture of diffusion. Next lecture is oxidation. Today we are running quickly through diffusion, and if you talk about diffusion, you have to talk about oxidation. So we talk about oxidation. But before I start with oxidation, this is part of a series of lectures that we talk about thin film processes where you add film or remove a film. When you add a film, it's called deposition. We can add a film by oxidizing the silicon, or we can deposit by chemical process from a gas phase. The names are epitaxial growth, if it's the same crystal, or chemical vapor deposition, or atomic layer deposition. In the liquid phase, like electrochemical plating. Also can be physical process like evaporation and sputtering. Or we can remove a film by etching, by a wet or a dry etch, or by polishing, chemical mechanical polishing. Those are all the processes that people use for thin film processing. But let's talk about oxidation. Oxidation is a key process for the semiconductor technology, and one of the reasons is that oxidation generates a very stable compound called silicon dioxide. Just some properties of silicon dioxide. First, it's amorphous, about 2.20 gram per centimeter cube. We have about 2.3 times 10 to the 22 molecules per centimeter cube. By the way, you can have also a crystalline SiO2. It's called quartz. It's much denser. So the crystal quartz has a 2.65 gram per centimeter cube, which means the thermal oxide is not so dense like the crystalline quartz. And it's an excellent electrical insulator. The resistivity is large, and a very large energy gap of about 9 electron volt, which means this is one of the reasons it's transparent. And high breakdown electric field can, with 10 times to the 10 megavolt per centimeter, or 10 to the 7 volt per centimeter, it's very stable structure. Now, SiO2, the oxide, every silicon atom is connected to 4 oxygen atoms, and every oxygen atom is connected to 2 silicon atoms. It's a tetrahedral structure, like a pyramid, and look at the distance of the side of this pyramid is 0.262 nanometer, or 2.62 angstrom, and the distance between the silicon atom to the oxide is 1.62 angstrom. Remember these numbers because later we have to put this structure on silicon. Now when you take these tetraheders, you see this is silicon, and this is the oxygen, and this is the silicon. What you can see here, that every tetraheder is connected to another tetrahedral by one atom. So this is a tetrahedral, and it's connected by this silicon atom. Now, every tetrahedral can connect to one atom, so they can rotate freely, basically. So if you have one tetrahedral next to one next tetrahedral, it can rotate slightly. The next one can be in a different position. So the whole structure has a short-range order, but there is no long-range order. You can find, for example, some structures with missing atoms, like here. There's this oxygen atom not connected to anywhere. This oxygen atom is not connected to anywhere. This oxygen atom is connected to, on one side, to two silicon atoms. This one is connected only to one silicon atom. So this one has an unsaturated bond. Now, the actual structure of the silicon dioxide also depends on the doping. If we add some doping into the glass, to the SiO2, we can affect the properties. However, we usually deal with very high pure oxide, and there is not so much doping in normal situations. But you can think about some contamination. For example, if you have like sodium. Sodium atoms, Na plus, are very, very small, and sodium can form an ion, and the ion can affect the structure of the oxide. You see, when people discovered glass, and people discovered glass 1,000 years ago, thousands of years ago, they found out that you can add some atoms to glass and change the structure. You can add some atoms to glass and change the color. And if change the color means you change the electronic structure. And you can add materials to glass and make it, for example, change the properties. So this is called glass modifiers, like phosphorus, boron, arsenic. And you can change glasses. The thermal glass is very pure, but if you add a small amount of sodium into the glass, you affect the properties of the glass. Remember this fact. Now, because it's an amorphous structure, you can have, for example, one tetrahedral connected to another one connected, then you have a free volume inside. So, typical thermal glass have some nano-sized volumes inside, some free space inside. So they're not completely in the densest possible structure. So you have some extra free volume inside the glass. The interesting part is that if you look at the interface, this is silicon, and on top of it is polysilicon. Now this is silicon is imaged in atomic resolution TEM, and you can see the periodic structure of the silicon. On top of it there is polysilicon, and you can see the periodic structure. In between, you see this area, it's random, it's SiO2. And this is very, very thin silicon dioxide, but most interesting, look at the interface between the SiO2 and the silicon. It's extremely sharp. Extremely sharp. The interface between the SiO2 and the silicon is extremely sharp. If I magnify it, what you can see is this is the silicon, and this is the silicon SiO2. Look at the interface. This is almost one layer of atom, and here it's a little disturbed, and here is a second layer of atom. So the transition between amorphous SiO2 and a single crystalline silicon is extremely sharp. And this is one of the reasons of the very high quality of the SiO2 and silicon interface. Another interesting effect you see at the distance is SiO2 is difficult to see the atoms, but every atom in the oxide kind of match every atom in the silicon. So in the surface, there are very small number of free electrons, of unbonded bonded which are not bonded. Bonded which are dangling, which are free. And this interface is not only very stable, it's also electrically stable. It's a very small number of bonds which are not bonded. Now, when you oxidize silicon, you generate silicon and you generate SiO2. Now, during growth, 1 mole of SiO2 takes up more volume than 1 mole of silicon. To grow an oxide layer of thickness D, a layer of silicon of a thickness of 0.44 D is consumed. Because for every atom of silicon, you add 2 oxygen. So if you consume this volume of silicon, you generate more than twice the number of SiO2. Now, this causes some stress. Now, look at the situation. Let's say that you have a silicon, the green one is silicon, and this silicon you have a volume of 1 by 1 by 1. Now, you know that during oxidation of a volume of 1 by 1 by 1, the volume grows by a factor of about 2. Because you know, I told you from the previous layer that 1 mole of Si2 take up more volume than 1 mole of silicon. So to grow oxide of D, you consume 0.44 D. So the volume of oxide that you grow is slightly more than twice than the volume of the silicon. So if I take this volume and I oxidize it, then it will generate a volume of SiO2 with dimension 1.3 by 1.3 by 1.3 by 1.3. If you take 1.3 to the power of 3, you will get about 2.2. But it's impossible because the volume next to it will also generate the same structure. And the volume in this side will always generate the same structure. So this volume, because this volume has neighbors from right to left, will stay 1 by 1 on the bottom. But since the total volume should be 2.2, it has to be about 1.2 to grow about 1.2. So the total volume will be 2.2. Because 1 volume of silicon generates a volume of 2.2 of silicon dioxide. And because it's a symmetrical growth, the growth in the right is the same as the growth to the left. Every volume, if it's 1 by 1 by 1, has to stay 1 by 1. So the only thing that happens is like squeezing a toothpaste. It will grow up. So the structure is stressed, is under stress. And every layer pushes the neighbors. Every region pushes the neighbors. So the structure is under compressive stress. Every neighbor is pushed by the neighbors. So the stress here is compressive or a negative stress. So every layer, the neighbor pushes in this direction. And this pushes this direction. But the push on every layer is compressive. Every layer is compressed from the sides. So this is very important to remember. When you oxidize silicon, you generate silicon dioxide, but you also generate stress. Now this stress can be relieved or not, depends on the situation of the oxide. If you grow the oxide at very high temperature, more than 1,000 degrees, then the oxide behaves like a viscous liquid or viscoelastic liquid. So it can flow. Then the stress is relieved. If you grow below 980 or 970 degrees Celsius, the oxide behaves like elastic material and the stress stays. This temperature of about 970, 980 degrees Celsius is the glass temperature of silicon dioxide. Above 970 or 980, the glass behaves like a viscoelastic material. Below, it behaves like an elastic material. And because it's elastic, it's like a spring. You push it, it pushes back. At high temperature, it's viscoelastic, so you apply the force, it can flow. because of symmetry. Let me plot it again here. This is your structure, and you oxidize. You put it in oxygen, and when you put in oxygen, you oxidize the silicon. This is your wafer. Then let's look at one volume. This volume is 1 by 1 by 1. Then you oxidize it. Because of symmetry, the neighbor is also growing. And the neighbor is also growing. But each one is pushing the neighbor by the forces cancel. The forces actually are counteracting. And each of them stay 1 by 1, but they grow to this direction. Because the volume should, listen, the volume should grow because we generated oxide. Now, luckily, oxide is elastic enough and can flow so it doesn't break. But if you grow, for example, if it was a much tougher material, it could break. It could get cracks. The temperature, okay, glasses, pure SiO2, thermal SiO2, the glass temperature is approximately 970 degrees Celsius. So above the material is viscoelastic. Below it's elastic. This is very typical to amorphous material that they have something we call a glass temperature. So it's still a solid. Here it's a solid, here it's a solid. But at a set, you can think about it as at a certain point all the bonds are connected. But if you heat up the structure, some of the bonds are released. Then the material behaves more like a viscous, like a fluid. It can flow. But it's still a solid. So it's a solid reflow. It's not a liquid. The melting point is actually something like 1400 something degrees Celsius. So it's not melting. It's just transition from completely elastic material to viscoelastic material. By the way, you can change this temperature. For example, if you add a little bit of phosphorus or boron, and sometimes you add both, you can reduce the glass temperature significantly. And with some common tricks in some companies, you can control the glass temperature, but you have to be very careful because PNB can also change doping of the substrate. But if you want to control the glass temperature of glasses, you add some doping into the glass and then you change the glass temperature. Yes? No, what I said, there's no reason. The question, why should we keep this temperature? What I said, is you grow in the temperature that you need. All what I'm saying is if you grow below 970, you expect to see larger stress in the oxide than if you grow. Some companies, I remember, they grew like at 1170 degrees Celsius just to eliminate the stress. But if you grow at very high temperature, then you have a lot of diffusion. You want to grow at low temperature because then you don't have a lot of diffusion. It's very limited. If you remember, another important temperature that I told you in the last week is the annealing temperature for solid state recrystallization in silicon. You can have complete solid state recrystallization in silicon and temperature between 525 to 800 degrees Celsius. So when you do ion implantation, you cause a lot of damage. But you can cure the damage when you anneal it in 800 degrees Celsius. So annealing is below the glass temperature. So the next step is oxidation. And you can choose. Basically, this is just, I did not say that we have to choose below or above. I just say we have to take it into consideration. Now, the oxidation can be conformal. if let's say we oxidize this structure, we can grow here and grow here and grow here. But you look at the side here, on the side here, and what you find out on the flat surface, for every volume we generate 2 volumes of oxide. On the sides, it's kind of complicated. Which side do we grow to the side? In this area, the contribution is from the 2 sides here. So actually, growth on a curved structure is complicated. Now, the reason, one of the applications for silicon dioxide is an excellent mask. For example, we know that the diffusivity of boron, phosphor, arsenic, and antimony in SiO2 is very slow. So if we take a silicon and we keep it in ambient with boron, phosphorus, and arsenic, it will go into the silicon, let's say we have a silicon dioxide, and by lithography we open a hole. So what will happen, we introduce dopant only in this region. Exceptions for gallium. Gallium goes very quickly through oxide, so it's not very useful. This is like thermal oxidation equipment. Typical equipment, some companies take like a boat and put the wafer on the boat and insert them horizontally. What you see here, this is the boat holder, and the wafers are going into the chamber. Or you can look at vertical, when the wafers are vertical, and it's called vertical furnace versus a horizontal furnace. Now, there are 2 major processes for oxidation. One process is called dry oxidation, is silicon plus O2 going to SiO2. This is called dry process. And the second process is silicon plus H2O become SiO2. And again, I need to balance this equation. It's 2H2 here. And we have 2 hydrogen coming out. I hope that you can see this, the 2 hydrogen coming out. And what you can see here, this is the oxide thickness in a wet oxidation versus time. This is 900, 1000, 1100. And you can see that you can grow up to about 1 micron after 1 hour. Dry oxidation, it's much, much slower. And it's interesting because you expect here to get a faster process, because here you have to break the bond of the hydrogens. You need more energy for this reaction. But nevertheless, oxidation in steam, of course, at 1000 degrees Celsius, this is not water, this is steam. Oxidation in steam is much faster. So this is called wet oxidation, this is dry oxidation. Typically for gate of transistors, we use dry oxidation because we can control the thickness. Let's say I want to, this is 100 angstrom, or this is 20 angstrom. If I want to grow very thin oxide, I grow with dry oxidation. If I want to grow thick oxide, I grow with a wet oxidation. Wet oxidation, the initial oxide thickness is very small. What people find out is for wet oxidation, the initial oxide thickness is very, very small. For a dry oxidation, if you plot thickness versus time in a normal scale, you find out that at t equals 0, if you take some measurement, you extrapolate, it's not going to 0. Which means, but this cannot be, because at 0 time the thickness is 0. So at dry oxide near 0, the behavior is difficult to extrapolate. Now let's discuss the model of oxidation. This model is called the Diel-Grove model. It's the same famous Andrew Grove that founded Intel. So he was also not only a good business person or engineer, he was also a very good scientist. So these are the dry oxidation process. This is the wet oxidation process. And the Dill-Grove model is as follows. If I would like to understand or to model oxidation, I have to make some assumption where is the oxidation. And there are two families of possible oxidations. One possible oxidation is that if this is the silicon, and let's say we already have a little bit of SiO2, is that the oxidizing species, let's say it's oxygen, the oxygen diffuses through the oxide and the reaction is here. Another possibility, like in iron, let's say we have a little bit of oxide. The iron diffuses and the reaction is here. And it's fundamentally different. Because when the oxidation is here in the bottom, the reaction is very slow, it's very well controlled, and it's very uniform. And the reason it's uniform, because let's assume that for some reason we got thicker oxide here. If you got thicker oxide here, the reaction here becomes slower, because the diffusion distance is longer, and then the reaction here becomes faster. So after a while, it becomes straight again. Because of some accident, a place has a slightly thicker oxide, then the reaction rate goes down. Because the diffusion from here to here now is longer. If you have this effect, it's basically the diffusivity of iron into here is very, and what I have to say here, I have an unlimited, high concentration of reducing agent. In iron, what happens, the reaction occurs here, and this mechanism, it can also happen, but because you generate stress, and actually what you do, you put layer on layer on the top here, and you are not going to have a uniform layer, and you all know that when you oxidize iron, you generate rust, and the rust is not so uniform. If you look at aluminum, for example, makes very nice oxide on top of it, and the oxidation of aluminum is stopped because the diffusivity of the oxygen through the oxide is very, very slow. Now, this was investigated. So how do you know if the silicon is going out or oxygen is going in? If you do this experiment, how would you know? Think. Try to think of an experiment. I'm asking you, tell me, where's the beef? Where is the reaction? Here and here. First, I can build a model and fit to the model. But let's say I want something more. Think you have to put some material scientists here. You have to put some markers. For example, anneal not in regular oxygen, but anneal with some isotope of oxide. So grow some oxide, and then change the ambient to some isotope. So if the reaction is on the surface, the isotope will appear here. If the reaction by diffusion, the isotope will appear here. So by using nuclear methods, people actually discovered that the reaction occurs here. And oxygen is diffusing through the structure, and the reaction is here. So once you know this effect, you can follow the flux of the oxygen atoms, oxygen molecules. Let's say there is a gas. And again, depends on the structure of your furnace. Yes? The reaction is on the surface, here. The oxidation reaction in silicon oxidation occurs at the interface between the silicon and the silicon dioxide. First is, let's say this is your wafer. And there's a gas flowing here. oxygen. What you have here next to the wafer, you will have an area which we call it a boundary layer. In this area is a transition between the moving gas and the wafer which is not moving. So you can think that initially, if this is the moving gas, and this is your wafer, the gas is actually transported from the entire volume of your furnace through the boundary layer to the surface. So first you have diffusion inside the gas. So you have a gas molecule here to the surface. Next to the surface, the oxygen dissolves into CO2. The oxygen dissolves into the glass, and because we have here the concentration in the surface, C0, we have some concentration in the surface, we have a diffusion from the high concentration to the low concentration. So inside the glass, we have a diffusion of the oxygen to the surface, and at the surface, we have the reaction. Now pay attention that I put here CS, which is the solubility limit of the species on the surface, but I say that actually, the actual concentration is C0. It's less than the limit. And the reason is, I will explain to you as follows. So Cg is the concentration in the gas. Cs is the concentration in the stagnant layer oxide boundary. So Cs is the concentration in the gas right next to the silicon. Now the concentration inside the silicon, C0, is less because of some solubility problems or issues. And then we have Ci, C0 is the concentration in the oxide at the stagnant layer oxide boundary. And Ci is the concentration in the oxide. Now we have a flux here from the gas to the surface, from the surface here to the surface to the interface here, and then we have a flux of atoms actually reacting, F3. F3 is how many atoms are reacting per unit area, per unit time. F2 is how many atoms are moving through the oxide by diffusion. And F1 is how many atoms are moving from the bulk of the gas to the surface. Now, in equilibrium, in a steady state, F1 equals to F2 equals to F3. So if you write again the equations, and we need to remember the famous gas equation, the concentration in the gas, or N, the number of moles per unit volume times the volume, is the pressure divided by kT. So this is Cg is Pg over kT. This is the equation of ideal gases. Now what we know here, we know that this is Cs. The concentration here is Cs is proportional to the pressure next to the surface over kT. Now, according to Henry's law, if I know the pressure here, and there is some, because you see, because we have a flux of atom here, the pressure here should be slightly less than the pressure here, because we have a gradient in concentration because of the reaction here, because some atoms are being consumed here, so some disappear. So we know there's a law called Henry's law, which means the concentration of the atoms in the solid is proportional to the pressure in the gas. The higher the pressure, the higher the concentration. This is called Henry's law. And this constant is called, this Henry's law states that C0, the concentration at C0, is H, Henry's law, times the pressure at the surface, or according to the gas law, HKT times Cg. So if we write this equation, we can immediately calculate F1. F1 depends on the difference between the concentration in the gas minus the concentration next to the surface. We say that the difference of the concentration between here and here drives the gas from this point to this point. Now, what is Hg? Hg is basically diffusion coefficient, because if you remember Fick's law of diffusion, flux is d times change of concentration versus delta x. In our case, d is d02, the concentration of the oxygen in the gas. Delta C is C gas minus Cs, and delta X is the thickness of the boundary layer, dO, ds2. So this is the explanation for this first equation. Now we call this expression Hg, because it's constant. Those are two constants. Constant divided by constant is a constant. So delta X, no, Fick's law says that if I have a gradient of concentration between 2 points, you have a profile. This is concentration versus X, and we have random profile. The flux here is given by this equation. So if we have 1 point is C gas, and the second point is Cs, we can estimate the flux by C gas minus Cs divided by delta X, which is ds2, and multiplied by the diffusion coefficient. So we calculated F1. But we want to manipulate a little bit the numbers to make life simpler, because I don't like this equation this way. I would like to write it in a slightly different way. So we know Cs is Henry's law times the pressure, so I know the ratio between Cs and C0. So I can define, if C0 is HPS and HPS is HKT CS, sorry, it's a typo here. It's this is PS. No, sorry. Sorry. There's some strange thing happened to the equation here. So forget this. Sorry. CS is 0 over HKT. Oh, actually, I'm sorry. Sorry, it's okay. It's okay. Now, we can definition. C star is HKT times C gas, so C gas is C star over HKT. So since before we defined F1 is Hg Cg minus Cs, we know that it's also H C star minus C0. Now, C star is kind of ideal number. It's what would be the concentration on the silicon at infinite time at solubility. This is C0 is an artificial value. It's not it's defined by Cg. C0 is a function of Cs. So if I define C0 as a function of Cs, I'll define C star as a function of Cg. So C star is a number that I define. Question? I lost you. C star is a function of Cg. What is C star? C star is a solubility, is a concentration in the solid if the gas concentration at the interface was Cg. Now this will happen if the reaction stops and I wait infinite time. C star is the concentration in the interface if the concentration in the interface, if Cs equals Cg. If Cs equals Cg, then C0 equals C star. It's another way to say it. It's an imaginary, not imaginary number, it's a kind of ideal number. So F1 is Hc star minus C0, and we define the new H is Hg over HKT. Sorry, I thought I made a mistake, but I did not, so I can define this new constant H as a function of Hg. And Hg is the mass transport coefficient in the gas, and C star can be assumed as the concentration at the SiO2 oxide interface if at equilibrium. So let's continue. This was about F1. Now about F2. F2 is much simpler to calculate because C0 is the concentration at the oxide upper surface and Ci is the concentration of the oxide silicon interface. So the flux is the diffusivity of the oxidant through the oxide times delta C, C0 minus Ci, over delta T, delta thickness, which is the thickness of the oxide. So this is the second equation. Now the third equation is very simple, but can be very complicated. We assume a first order reaction, which means the reaction rate, F3, is proportional to the concentration of the oxidant at the surface. In a steady state solution, all three fluxes are equal. F1 equal F2 of 3. So let's write them again. F3 is K3Ci. F2 is d C0 minus Ci over T oxide. Yeah, T oxide is function of time. Yes. This is exactly what I do. What I do, I found, if I know F1 equal F2, F3, I solve for F2 as a function of T oxide. But F2 as a function of T oxide is also a function of F1 and F3. I can show it to you. I gave you the final solution, but let me write the three equations here so you can remember it. First equation is F1 is H C star minus C0. Second equation, F2 is D times C0 minus Ci over D oxide, which is a function of time. And F3 is K3 times Ci. Now, we have two unknowns, or three unknowns. We have C0, we don't know, Ci, and D oxide. So I'm sorry? K, risk. K3 is a constant. K3 is a constant which is a function of the reaction rate. It describes the reaction rate. It's typically exponential function, a function which exponentially increasing with temperature. Depends on the reaction rate at the surface. So when I solve F1 equal F2, I can find F. See, I have here three variables. So I can solve. I can always eliminate 2. If I have three variables and I have two equations, I can eliminate 2. So what I do, I find F as a function of D oxide. Because I can eliminate C0 and I can eliminate Ci, but I will stay with T oxide. So if I'm doing it, I find out that F becomes constant, time constant, and constant, divided by 1 plus Ks over H plus Ks T oxide over D. I find F as a function of T oxide. And when I do this, I find that it's an expression of a constant 1 plus constant times the oxide times constant. I will erase this because this is not properly written. But what you find out is when the T oxide becomes thicker, the reaction rate is going down, the flux is going down. But then you can solve the equation, because what is F? F is how many atoms arrive at the surface per unit area. Then I divide it by N. N is the number of oxidizing species molecules per unit volume. So the number of atoms per unit area, per unit time, divided by the number of atoms per unit volume is thickness per time. I will write the units here. Flux is number of atoms divided by centimeters square per second. If I will divide it by the number of atoms per unit volume, I will get centimeter per second, which is the change of thickness versus time. So what is NL? If it's a dry oxidation, then NL is the number of molecules needed per unit volume, which is 2.2. If it's a wet oxidation, I need twice the number of oxidants because I need 2 molecules of water. So what I found here, now this is an equation which is very easy to sample. dt oxide over dt, which is the growth rate. This is the function. What I need to do is just integrate it. So if I do the integration, I skip some steps. I'm not doing the integration. I assume that all of you know how to integrate, because what you should do, you take this expression and move it to the left, take dt, move it to the right, and do the integral of dt oxide times this function between T oxide 1 to T oxide 2, and do integral in the time between T1 to T2. So I can find an expression. What you find out that T oxide square plus AT oxide plus equal B times T plus tau. Tau is a constant which depends on the initial oxide thickness, A and B. Now B is some constant and A is a constant. Now if you look at the expression here, you see that you have here a ratio between Ks and H and a ratio between Ks and D. What you find out that B depends on D H Pg over N1, and A depends on D 1 over Ks plus 1 over H. There is an explanation for this, because Ks is the reaction rate at the surface, and H is the transport coefficient in the volume. Now usually if you have 2 processes in series, the slower one is the one which is the one which determines the reaction rate. So if Ks is large, then H is dominant. If H is large, then Ks is dominant. So always the dominant value is the one which is the lowest, which is the slowest. So this is the famous Diel-Grove model, which says that the oxide thickness square plus AT oxide is equal B times T plus tau. So this is the model for oxidation. This model is only for 1-dimensional growth. If you want to do a 2-dimensional growth, more complicated, because if you grow an oxide, let's say you start with silicon and then you grow, you put SiO2 on top of it, you etch it, then you grow it again. Now in this area, you will grow less, because here the initial oxide thickness is more. So here, in areas 1 and 3, the growth rate is slower. In area 2, the growth rate is faster. And because of that, after let's say you remove the oxide, you will get etch in the silicon. And this is, by the way, an old trick to, if you want to mark your silicon and you don't want to etch it, you grow an oxide, you etch what you like, you oxidize again, and then remove the oxide. And you end up with this green interface. And this was in the exam last year. Remove it from the video to guess the shape here and to give the value here. Now, pressure effects. So we found the coefficient B over A. And why do I look at B over A? Because we have 2 regimes. One regime when the oxide is very, very thin. When the oxide is very, very thin, then I don't care about this term. For very thin oxide, T oxide is B over A times T plus tau. For thick oxide, I can say T oxide become square root of B times T plus tau. So usually, people don't look at A and B, but at the constant, the constant B, they call it the parabolic rate, and the constant B over A is always called the linear rate, or the linear constant. So the linear constant B over A, if I take B and A from this equation, B over A, and divide them, I will find it depends on CA. CA is the pressure in the ambient or depends on the pressure in the gas. So if I want to increase the oxidation rate, I increase the pressure in the gas. That actually makes sense. This is thin, this is thick. If you look at this expression, for thin oxide, I eliminate the square value. For thick oxide, I eliminate this value. Another interesting effect is for heavily doping. If I oxidize, let's say I have a structure of N plus over N. This is a structure, for example, for contacts. For a contact, you have N plus over N. And you measure then you oxidize the structure. What you find out that over N plus, the oxidation is faster, slightly faster. And by the way, also the diffusion coefficient here will be higher because of this oxidation. But it's interesting that B over A increases, while B remains almost constant. So the effect is only over B over A. Highly doped silicon has more vacancies, or create more vacancies. Now we have some, let's talk about some effects in oxidation. The oxidation depends on the orientation. If you oxidize the 111 silicon, you get different oxidation rate than 100 silicon. Actually, 111 silicon oxidizes faster than 100. It's an interesting effect. 110 oxidizes less than 111 and faster than 100. It's the other effect. Now, situation can be more complicated. Let's say you take a silicon and you etch it and you generate a pillar. Somehow you take your silicon and you etch it very nicely and you have a pillar. Then you start to oxidize it. Now the pillar, if let's say your silicon was 100, let's say 100, so this is 100, 100, or 010, and this is 001. But if you look at the surface of this pillar, it has not only 100 and 110, it also has some angles which are like in 45 degrees. So what you find out, that you actually, on these areas, you grow a thicker oxide than here. So actually, what you get, if you look, this is a round circle, and this is the 100, so this would be like the 010. When you oxidize it, it will grow like this. On the sides, it will grow faster than here. Because this is 111, sorry. Or 110, sorry, not 111, 110. And 110 plane grows faster than 100. And the reason is, if you remember FCC structure, 111 is the densest structure, more atoms. Because you have more atoms per unit area, then it grows faster. And the 100 is the less dense structure, less dense plane in the silicon. You can play games. This is how it looks, actually. People actually did it, believe it or not. And you have to, the problem is this is, I neglected here one thing. And what did I neglect in this assumption here? Stress. Stress. Now, you remember the Le Chatelier principle in chemistry? Somebody can quote Le Chatelier principle in chemistry? If I have a chemical reaction, and I apply something that changes this reaction, what will happen? The reaction will go in a direction to reduce this effect. So if I generate here more stress, or I generate here if there are areas which generate more stress, and in the corners I will generate more stress, then the reaction rate on the sides will be slower because of Le Chatelier principle. And this is why, if you look here in the corner, you don't see much this effect. You see the oxide here is quite round. Not what I plotted here. And the reason is that if the reaction was just depends on the crystalline structure, then it will go faster on the sides. But here, because it grows faster, it has more stress. Then on the sides, the reaction rate goes down, and we get this nice circular shape on this oxide. Now, if you really want to model it, it's complicated because all the coefficients that I described to you before, Ks, diffusion coefficient, are all functions of the stress. And the stress depends on the growth rate. And the growth rate depends on this function. So you understand that I described to you only, I would say, the simple model, not taking into consideration secondary effects, which are very significant for nanostructure or for very small structures. Another interesting oxidation, and this is about the end of the lecture, is oxidation of polysilicon. Polysilicon also oxidizes very nicely, but polysilicon has like one crystalline and the second crystalline next to it. And between the two crystals, there is an area which is kind of a transition region. We call it a grain boundary. In this grain boundary, the silicon is less crystalline, and it oxidizes faster. So when you oxidize polysilicon, it follows the same Dilgrove model, but it becomes rougher. So you have to remember this when you oxidize poly, which is a very common process. Another oxidant is a mixture of oxygen and halogen, chlorine. It became very useful in the past because if you have some contamination in your chamber, let's say sodium, imagine chlorine at 900 degrees Celsius. This is like the ultimate cleaner. The chlorine at very high temperature is extremely reactive gas. It reacts with, if you have some residues of metals or sodium, it makes the system extremely clean. But also, chlorine has the effect of cleaning of heavy metals and gives a better interface to silicon substrate. You can use either HCl, direct straight HCl, which is very difficult to handle, or some organic gases with chlorine. The problem, they're quite toxic material. Just be careful when you do it. I mean, for example, we used TCA in the past, but it created phosgen, mustard gas. So you have to be careful with these gases. And let's go back a little bit from the processing lecture to the device level. When I grow an oxide, I have an interface between the oxide and the silicon, and I can have a charge here. Charge typically is positive. But I can also have sodium and potassium because of some contamination, and they have a strong effect on the reliability of the oxide. So we need to remove it, and adding chlorine removes the sodium and potassium and stabilizes the structure. This oxide, let's say this is silicon. This is beautiful hexagon silicon. It's just a sketch. The oxide is an amorphous material. This is silicon oxide, silicon oxide. I can have charge inside the silicon. This amorphous silicon, I can have a charge inside the oxide. And there is a very famous kind of fact that was discovered by Dill, and he discovered the following. If I anneal in nitrogen, then I have a low charge density of this number is less than 2 times 10 to the 11. If I anneal in dry oxygen, at low temperature, I have a lot of charge. The higher the temperature, the lower the charge. If I oxidize in steam, I have more charge. So it was discovered that if I want to have a low charge density, I need to anneal or nitrogen or in dry oxygen, but not in steam. It's an experimental fact. This is why for gate oxidation, today, people don't use steam, or at least in the past. Of course, you have an exceptions, but or if you use steam, annealing nitrogen at high temperature. And today, people also add another step, annealing in a mixture of nitrogen and hydrogen. It's called a forming gas. And this annealing is typically at much lower temperature, even 300 and 400. So this is called the Diels temperature triangle. And basically, to minimize interface charges, use argon or nitrogen, and also have a final annealing step at 400 or 450 with a forming gas after the metallization step. So I have here some slides about the local oxidation, which I skip. And I will finish with one interesting fact. All the models I described to you before are good for oxide more than like 20 or 30 angstrom. If you want to grow really thin oxide, you have the following fact. Let's say you plot, these are plots of oxidation versus time. This is 950, 1000, 1050. This is, and if you notice, the oxidation versus time is kind of a parabolic, kind of it can be linear or going like square root of time, which fits nicely the Diels-Grove model. Diels-Grove model describes this function, can be linear or parabolic or a square root of time. So it fits nicely the data. So if you look at the oxide thickness versus oxidation time in a log-log scale, you expect to find a straight line because it follows either time to the power of 1 or time to the square root of time. But what you find out, with very, very short time, this is 10 to the minus 1 of a second, of a minute, sorry, this is 1 minute. You find out that for very short time, the model doesn't fit. The model is different. For very short time, for the first 10 angstrom or 20 angstrom, Diels-Grove model doesn't fit. And the reason is, Diels model assumes one-dimensional diffusion. But you have a very thin layer, the molecules can diffuse but also move laterally and still have a significant effect. You have to introduce more sophisticated model. Now, there are a lot of models, and the best model is that at a very thin layer, you add another term, which is exponential term. So dx oxide over dt. This is the old Diels-Grove model, b over t ox oxide plus a. But you have to add some two exponential terms, which I would say they're more experimental. There are a lot of papers explaining them, but they're experimental based on experiment. They are experimental based on experimental data. And it's called the thin oxide correction. So you plot the dx oxide over dt is this function, which is 1 over t oxide, but also two exponents, which are decaying very rapidly. The typical L1 is 1 nanometer, and the second one is 7 nanometer. And when you do this, you find this expression. I added here some of the oxide models. There's quite a number of models. For example, for very, very thin oxide, maybe the oxide is not complete. So you have some roughness, or you can have some kind of or nanopores through the oxide. So you have to include them. The other models of tunneling effects. For very, very thin oxide, you can have some charge effect and tunneling effect. I will skip this in this lecture. And basically, there are a few more things that I'm going to in future lectures, I'm going to talk slightly about dopant redistribution and about the basic CMOS technology and MOSFET, and about before we go home, I want to give you the biggest problem today. The biggest problem today is that if you have, this is a cross section in a MOSFET. This is the silicon. This is the gate oxide. If you look at this is the channel, and this is the polysilicon, and here we have an oxide. And this is, for example, a 40 angstrom oxide. If you go for very thin oxide, this is, you take a very thin oxide and you apply voltage over the oxide. And this is oxide thickness, current, versus oxide voltage. If the oxide is 10 nanometer, 100 angstrom, you get this beautiful curve. It follows some rules. It's called the Fowler-Nordheim model. It's actually, you find out that it's 5 volts, or this value is very low. If you go to below 5 nanometer, you start to see this effect. That it's like at 3 nanometer, suddenly here you get very high currents. And it does not follow, it does not go down like this. It's actually, it goes in a different model. So below approximately, below gate voltage of about 3 volts, and below thickness, and for 3 nanometer, you start to have a direct tunneling between the top plate to the bottom plate. Electrons are just tunneling through the oxide. So very thin oxide, like if you take a 2.5 nanometer, and you apply like 1 volt, you get 10 to the minus 2, about this value of, the tunneling current of about 10 to the minus 2 ampere per meter square. So you start to get very high current. So you cannot, if you grow like, this is 2.5 nanometer, if you grow like 1 nanometer, the current will be enormous. The gate is no more an insulator. So today, modern devices are actually replacing the very thin SiO2 with a much thicker layer of other materials like hafnium oxide or similar materials, which are much thicker, but with the electric constant which is much higher. So the gate leakage problem is also a power, and this is what you find out. This is the gate leakage. This is the power loss due to gate leakage. It's a function of time. This is 2000, 2010. And this is the actual active power loss because of the circuits. What you find out that approximately now these lines converge, which means now if we use now SiO2, then we'll have a big problem of too much current through the gate and too much power loss. So today people switch to high KD electrics. Like for example, instead of using 1.2 nanometer SiO2, you can replace it with a 3.0 nanometer of a material with a higher dielectric constant. So the capacitance will be the same. But here you don't have tunneling, because now you are back. The two electrodes are separated. So the way to solve the tunneling through the gate oxide in SiO2, and this is the 20 nanometer process, which is very old, maybe 4-year-old. You get a high K process. The capacitance increases by 1.6, but the leakage is 100 times less. Now you defined, we defined now something which we call EOT, electrical oxide thickness. Is effectively oxide thickness as you find by the capacitance measurements. So this is the high K process that everybody is using. If you open today, if you go to very modern processes, especially for microprocessors, you will find out that the gate oxide is replaced. It's not SiO2 anymore. It's a material like hafnium oxide or similar with a much higher dielectric constant. So this is the high K dielectric. The other things people do is they put a metal gate replacing the polysilicon, but this I will describe to you again in the lecture number 12 or 11. Thanks.